Okay, good morning, sir. We are going to discuss about the parallel reactions today. It's a line shortage. So we start with the parallel reaction. The parallel reactions, it is nothing but if you take example of A is the feed and it's the reactant, and this gives a product. It's for example R, and similarly A gives S. So this we can also say like this, for example R and S. Because this like this, sometime they will write this, and here the same feed can give so many number of products. So this is what actually usually happen in the chemical industry, where you get multiple products. So this is common, and in this, one of the product would be the desired product and another would be an undesired product. Because we need or, for example, then this could be your desired product, and the yes could be the undesired product. Okay, like this there would be so many parallel reactions. For example, A gives, we say T, so there is another undesired product. So in this, maybe R would be the desired and other two would be the undesired product. Okay, we consider first K1 and K2 for only these two first. So we don't take it much many parallel reactions. We only consider two parallel reactions for for the initial stage. And if you see here, the rate for this particular reaction mechanism is R, that is for the product, okay, equal to K1 Ca, that is with respect to the concentration of A. And we consider this is a first order, okay, so we say first order, or we take it in a A1 order. So we say A1 here, or N1 doesn't mean, okay. And for the similar cases with the next product with the same, okay, we say that A2. Okay, this is for the ratio. For the product. So with respect to the product, you write the rate equation. Or if you write for RA, then it will be K1 Ca power A1 plus K2 Ca power A2. So this could be the rate equation for, because here it's a minus because it's a disappearance. So this could be the rate equation for A here. So you have sum of both two rate. Okay, this is what the actual rate law that you can write for the parallel reaction. Okay. Now we are going to see how the desired product, how the desired product can be enhanced in this particular mechanism. If you take a ratio of, so the ratio of the rate of R formed and the rate of S formed. This is what called the selectivity. They say selectivity. The term, the technical term is a selectivity here, and this selectivity means the ratio of the desired product. We consider R is the desired product to the undesired product. S is the undesired product here. Okay, so if you take this ratio, it is called the selectivity. Okay, in this, if you write the particular rate law here, So how this selectivity get enhanced for the desired product? If A1 is greater than A2, what will happen? That means RR by RS will be more dependent on, you forget about K1, K2 here, okay, more dependent on Ca power A1 because A2 is very less. So this is more dependent on the concentration of the first reactant. So it is more dependent on the Ca here. If A2 is greater than A1, what will happen? RR by RS equal to, so it is not equal to, it is proportional to Ca. Class of 3. So if, sorry for disturbance, if you take this particular ratio, then it is Ca power A2 because A1 is very small. If it's a very small, then this value will get diminished. So it is actually inversely proportional. So from this data, what do you acquire is that for A1 is higher than A2. That means the individual order of this particular first reaction mechanism is high when compared to this mechanism. Then the concentration of the feed should be very high in the reactor. If it's a high concentration is available in the reactor, then the desired product rate will be higher compared to the undesired product rate. Okay, if the rate of the undesired, if the order of the undesired product is higher than the desired product, if you substitute and see here, then the concentration of the A should be minimum to have a high desired product formation here. So this is what you see here. So what is the meaning? The meaning behind this is that you need a high concentration of A here. You need a low concentration of A here. That means you need a high concentration to choose the high concentration reaction mechanism. Then the reactor should be at the high concentration. So we always prefer for the high concentration, it is PFR or a tubular reactor. Okay, so the tubular reactor or the PFR would be preferred for the high concentration reaction mechanism. If you go with the lower concentration, it is preferred to have the MFR or CSTR in practical. Okay, this is what the dependence of the concentration with respect to the rate. Okay, if A1 equal to A2, then what will happen? A1 equal to A2, then does not involve on anything. So if this both reaction mechanism gives same order, okay, then if this is the case, then RR by RS will be more dependent on K1 by K2. So it is more dependent on we say T1, but it is T2. So this is more dependent on K. So the K is more dependent on the temperature. That means it is proportionally each other on this. So that means the temperature parameter will play a main role in this selection of the selectivity. Okay, so to have a higher selectivity, the temperature parameter would be very much influenced if you consider with the same order for the both parallel reaction. Okay, this is what the general case we have studied now in the beginning. Okay, by changing, so that means with this effect, if here again, if you plan to see that if K1 and K2 is greater than 1, that means the K1 is higher and K2 is lower, then you actually have a high desired product. Similarly, if it's vice versa, then low desired product. So this is what the term you from this particular K value. Okay. Apart from the temperature, the catalyst influence is also happen if you have a catalytic process here. So the both parameter, temperature and the catalyst. So these two have the influences if the order is same for the both parallel reactions. Okay. So the temperature and the catalyst are the main parameters that have the influences in the parallel reaction. Okay, most often you have to remember this. So what is happening if the reactor is not if A1 equal to A2, what type of reactor you can choose? That does not matter here. That is not at all considered about the reactor type here in this case. But for these two cases, you can easily choose the reactors. But for this case, the reactor type is not fit here. So you can choose any type of reactor depending on your economical and your requirement in here. Okay. So before we go a little deeper into this, I have to just explain two more terms in the selectivity. So selectivity, now we write as a selectivity first. So it is a parallel reaction. In terms of rate, we have mentioned in the selectivity here, but actual selectivity means how it is that it is the mole of the desired product. So the mole of the desired product with respect to the mole of undesired product. Okay. So this is the actual form of the So this is the actual definition of the selectivity. Here again, there would be two possible because you have a two reactor. For example, you have a tank and you have a tube. For example, you have Ca0 is the initial concentration of any reaction mechanism for A gives some R and A gives some S. So this you take the reaction mechanism, for example, here, and you have Ca0 inside, and you always consider Ca because depending on the concentration of A, we can easily identify how much it's been converted. Okay. So again, we take it here. But how the concentration it is been in the reactor. In this particular like MFR, if you take here, the concentration will be Ca, same Ca as like your outlet. That means in the tank and in the outlet, the concentration will be almost same. So there is no change at all. Okay. So that is why the concentration in the tank is low when compared to the initial concentration of the feed. But in this case, the concentration keeps on decreasing. Okay, so the concentration it is keep on decreasing with respect to the length. So if you take the length versus concentration, it is keep on decreasing. So that means at the initial stage, the concentration is very high. At the initial stage, the concentration is actually very high, and slowly goes down with the reactor here. So that means the concentration is high in some part and the medium in some part and then low in some part. That means the concentration is differed in the reactor. So to actually consider this in our case, you cannot simply say the selectivity in the overall here. So you have two types of selectivity. One is an overall fractional conversion term, or we'll take the yield. There is an overall fractional yield. Overall fractional yield, it is nothing but overall fractional yield and instantaneous fractional yield. Yield is nothing but how much A gets converted, okay? In terms of selectivity and the yield, you can in terms of selectivity, you talk about product, but in terms of yield, you talk about the feed material. So yield can be written as moles of A by moles of here with respect to the desired product. So moles of R, okay, R to the moles of A. So this is the overall yield, overall. So this is how you used to calculate it. But here, if you take two different things, one is an overall fractional yield and another is an instantaneous fractional yield. We say this is phi and this is psi. Okay, you consider as a phi here and then psi here. So this would be like a phi here. And what is psi? Psi, it is the same like this. Psi is same as the mole of R at that point. We said at that point, at that particular point, divided by mole of S A at that point. That means if you take 1 point here, or you take 1 point here, and you take 1 point here, in all these 3 points, you take all these 3 points, the concentration of the R would be same. So for this case, the overall yield would be same for the mixed flow reactor. And similarly, if you consider instantaneous, it gives the same value. That means psi equal to phi. So instantaneous and the overall yield will be same for this particular reactor, mixed flow reactor. But if you take for the PFR, for example, you take this point, you take this point, and you take this point and this point. All this point, the overall fractional yield would be psi or phi. So what will happen with the psi, I mean phi here? That means with respect to the concentration, Ca0 to CAF, I'll take this off, CAF, dCA, okay, so dCA is the, sorry, we put the psi here, psi dCA. Because the instantaneous concentration will keep on change with respect to change in concentration. Okay, this is what the actual connection between the the overall fractional yield of an outlet reactor to the instantaneous fractional yield of that particular system. Okay, and here they will consider one more thing, that they will put 1 by delta Ca, because this is a long derivation. I don't want to go with the derivation here. I just want to say what is the reason behind here. Okay, this is what the actual connections between the phi and then psi. Okay, once you start this, we have we have so many discussion on this, and we are going to see one by one. Okay, so first of all, we will do a problem with these parallel reactions, and then I'll tell you how to apply the formula here. So the parallel reactions. So we will go with the problem now, that the reactant A in a liquid produces R and S. Reactant A produces R and S. Okay. By the following reaction mechanisms of a first order with following: A gives R and A gives S. Okay, this is the two mechanisms that has been. And it's a first order. Okay, so this is the first order. Okay, here a feed with Ca not equal to 1, Cr not equal to 0, and Cs not equal to 0. So that means the feed will have a Ca naught 1, Cr naught and Cs. These two are the product, or initially there is no product in the system. Enters in mixed flow reactor, enters in mixed flow reactors in series tau 1 equal to 2 minutes and tau 2 equal to 5 minutes. Okay, the composition of first reactor exit is Ca equal to 0.1, Ca1 equal to 0.4, Cr1 equal to 0.4, and Cs1 equal to 0.2. Now the question is, find the composition of second reactor exit. So you have two reactors. Ca not equal to 1, Cr not equal to 0, Cs not equal to 0, Ca1 equal to 0.4, Cr1 equal to 0.4, Cs1 equal to 0.2. And they are asking Ca2, Cr2, Cs2, Cr2, Cs2. You need to find all these three. So here the volume is not given, but they are given tau 1 for this and tau 2 for this. So this is what the volume value here. So you use the performance equation and then find out the Ca2, Cr2 and Cs2. We know tau value. When, for example, you write the performance equation here. Performance equation is nothing but for the MFR in terms of concentration. So we will write the performance equation in terms of concentration. For example, we take tau 1 for the MFR 1. Okay, this is 1 and this is 2. So for 1, tau 1 equal to so it's very simple that Ca0 minus Ca1 equal to Ca1 by minus Ra. So what is Ra here? Would be, this is the two reactions. So K1 Ca plus, because this is a K1 here and K2 here. You have K1 and K2. You have two parallel reactions. So K1 Ca, and you know that both are the first order. K2 Ca. As it is A1, you put Ca1 and Ca1. Substitute this here and find out the K1 and K2 value. Find out K1 and K2 value, because here I'll just see whether how we are doing the K1 and K2 value calculations. So find out K1 and K2. Once you find out K1 and K2, then you go with the second reactor, tau 2, and you know the tau 1 and the tau 2 values. And you go with the Ca1 by Ca2 minus Ra2. Minus Ra2 is same like the previous one. K1 Ca2 plus K2 Ca2. If you know this value, then you can find out Ca2 here. If you find Ca2, then you can also find out Cr2 and then Cs2. Yeah, please do it and send me the answer Ca2 here. I need the answer for Ca2. Mr. Karthik D, 45. Mr. Karthik D, 45. Sir, Mr. Kavin Prasad, 43. Mr. Kavin Prasad, 43. Sir, are you doing the calculation? Value for Ca2.